In this video, I will be discussing how to do problem number 4 from midterm 2. The fundamental principle we will be using for this problem is the energy principle. This principle states that the change in energy of a system is equal to the work plus the heat transfer. We can find the total change in energy of the system by calculating the sums of all the different changes in the energy of the system. The problem states, you put a thin metal pot containing 2 kilograms of room temperature or 12 degrees Celsius water on a hot electric stove. You also stir the water vigorously with an electric beater, which does 100 joules of work on the water every second. You observe that after 15 minutes, the water reaches a temperature of 100 degrees Celsius. The specific heat capacity of water is 4.2 joules per gram Celsius. Part A asks, what was the change of thermal energy in the water? The equation change in E thermal equals mc delta T can be used to solve this problem, where m is mass, c is the specific heat capacity, and delta T is the change in time. After we plug in the given values into this equation, we get that the change in thermal energy was 739,200 joules. Part B asks, what was the thermal transfer of energy Q into the water from the surroundings? We will start from the fundamental principle, the energy principle. We know that the change in energy is equal to work plus thermal energy transfer. Since thermal energy is the only energy that is changing for our system right now, we can assume that the change in thermal energy equals work plus thermal energy transfer. Next, we must rewrite the equation to solve for Q so that we have Q equals change in thermal energy minus work. In the problem, we are given work per second. To calculate the total work done, we multiply this by the time it took, which happens to be 15 minutes or 900 seconds, thus giving us our total work, which is 90,000 joules. We then use the change in E thermal that we calculated in Part A and subtract the work to get the thermal energy transfer, which turns out to be 649,200 joules. For Part C, we are asked to find the change in energy of the surroundings. We assume that the total change in both our system and the surroundings is equal to 0. Since the change in energy of our system is the change in thermal energy, we know that the change in the surroundings is equal to the opposite of our change in thermal energy, thus making the change in energy of the surroundings equal to negative 739,200 joules. Part D states, you take the pot off of the stove and drop it in 2.26 kilograms of sweet potatoes. The potatoes are initially at room temperature, 25 degrees Celsius, and have a specific heat capacity of 3.14 joules per gram Celsius. Determine the final temperature of the water and the sweet potatoes once they come to equilibrium. You can assume that the pot is a very good insulator and does not change temperature. The fundamental principle states that the change in energy is equal to work plus the thermal energy transfer. We know that the change in thermal energy is equal to 0, therefore the change in E thermal of the sweet potato plus the change in E thermal of the water must be equal to 0. After plugging in the equation change in E therm equals mc delta T for each part of the system, we can calculate the final temperature of the water. We find that the final temperature is equal to 65.7 degrees Celsius. Thanks for watching.